Okay, so here I have a 5 by 5 matrix that has 2 eigenvalues. So remember, I need to be able to find 5 eigenvectors. So one eigenspace, so that means that vectors that span the space, one of the eigenspaces, so for one of these eigenvalues is 3-dimensional. So I get 3 eigenvectors, okay? The other eigenspace is 2-dimensional. So I need to know, can I make up my PD P inverse, that's what diagonalizable means, with this information? So this tells me I have 3 eigenvectors, this tells me I have 2 eigenvectors. That makes the P a 5 by 5, and then the D would be the diagonal with these 2 eigenvalues. So yes, because I have 5 linearly independent eigenvectors. So PD P inverse can be created. Okay, so here I have a 3 by 3 matrix with 2 eigenvalues, and each eigenspace is 1-dimensional. So every eigenvalue has at least one eigenvector, right? So I know that each one of them is 1-dimensional. Is A diagonalizable? Can I do the PDP inverse? No, because I only have 2 eigenvectors, right? And I need a 3 by 3 P and D, right? There's not, well, P for sure. So P is the one I'm really interested in. P is supposed to be made up of the linearly independent eigenvectors. There's only 2 of them. I can't make a 3 by 3 matrix. So that is no, it is not true. So here I have a 4 by 4 matrix with 3 eigenvalues. So each one of these eigenvalues is at least 1-dimensional. So here it says this one is 1-dimensional and one of the others is 2-dimensional. So is it possible that it is not diagonalizable? One is 1-dimensional, one is 2-dimensional. The third must be at least 1-dimensional. I spelled that wrong, sorry. So this A must be diagonalizable. All right, so let's play with some algebra with this. Okay, so I know that A is diagonalizable and invertible. Okay, so diagonalizable means A equal PD P inverse. So then show A inverse, I guess I said this not so clearly, is diagonalizable. We already know that it's, I did that wrong, didn't I? Diagonalizable. Okay, I already know that A inverse is invertible, right? So I just need to show that A inverse is diagonalizable. So that means in some way I have to get to that, right? That's what I'm thinking. Got to get to somewhere, get to that. So let's take this true statement and think about it. So if I know that A is invertible, what do I know if A is invertible? If A is invertible, that means lambda equals 0, or sorry, lambda does not equal 0, right? Because if lambda equals 0, then it is not invertible. Okay, so lambda doesn't equal 0, so doesn't that mean D is a diagonal matrix without a 0 entry on the diagonal, right? Because the diagonal entries are the lambdas, and so that means that there's no 0 on the diagonal. Okay, so I need that because if I'm going to take the inverse of both sides, so let's do PD, P inverse, inversed, right? So I took A, I know is invertible, so that's just A inverse. So what do I know about here? Remember how to play with this? You switch the order, right? So this is P inverse, inversed, D inversed, and then P inversed. So I switched the order. So what do I know about P inverse inverse? So that's going to be P. D inverse. I know D is invertible because it's diagonal, right? And wait a minute, what don't I know? Well, yeah, I know D inverse exists because it is diagonal, and so it exists. And then this is P inverse. So, don't I have it? I know that D inverse must be diagonal because D is diagonal. So here I have it. So I'm just going to let, let's just pick a different letter, let Q equal D inverse. So what I have is A equal P Q P inverse. So this A inverse, right? A inverse is P, this P. I changed D inverse to a Q, and then P inverse. So I've just made a different letter, but it's PQ P inverse. So that shows it's diagonalizable. All right, so let's go to the next one. Let's show if I have, oh, let me go back. Let me stop there.